So for this problem, I want to find the general solution to the differential equation 1 plus x squared times dy by dx is equal to x tan y. I want to give the final answer in the form y equals f of x. So we need to quite a few stages for this one. And we've got a trigonometric function in here, and with the differentials we're going to be integrating, so it's going to use quite a few different rules. Well, as per usual with the differential equations, we need to separate our variables, in this case y on one side, x on the other, leaving the dy where it is. The tan y is going to become 1 over tan y. Deal with that shortly. So 1 over tan y dy. The x can stay where it is. The dx comes up as a multiplier. This 1 plus x squared can move down as divisor. So you've got x over 1 plus x squared dx. Well, let's rewrite 1 over tan y. 1 over tan is cot, so you've got cot y dy is equal to x over 1 plus x squared dx. So we've isolated our variables. We've changed 1 over tan into cot. Now we need to integrate both sides. We're going to integrate cot y with respect to y and integrate x over 1 plus x squared with respect to x. And each of these has its own problems. So let's look at the integral of cot y first. Well, if we're going to integrate cot y with respect to y, you need to remember that we need to rewrite cot as cos y over sine y. And the reason we need to do that is because what this really means is if sine y is our function in terms of y, cos y is the differential of that function. So you've got the differential of the function over the function, which you are then integrating with respect to y. And whenever you have a situation like this, it means you end up with a natural logarithm of the function. So in this case, sine y. So that's going to be our solution for the left-hand side. We then have to deal with the right-hand side. So we also need to integrate x over 1 plus x squared with respect to x. And actually, this is quite similar to the last one. Because if once again we treat our function as the denominator 1 plus x squared, if we differentiate this, we would end up with 2x. So our integral is very nearly the differential of the function over the function. However, this would give us this extra factor of 2, which we don't have here. So to get rid of that, we need to multiply it by a half. So when we integrate, we end up with our half. The differential of the function over the function gets us our natural logarithm of the function, which in this case is 1 plus x squared. So we've done the majority of the hard work now. We need to substitute in our two solutions, such that the integral of cot y with respect to y is ln of sine y. The integral of x over 1 plus x squared with respect to x is a half ln of 1 plus x squared. And both of these will generate a constant of integration. So we can put a plus c there. We don't really like the c, so we can also say that c is equal to ln k, where k is a constant. So in our next line, we just replace the c with an ln k. So we've done our integration now. We've replaced c with ln k, but we haven't yet got it into the form with y as the subject. So that's our next stage. Well, let's use some log laws and combine these together such that ln of sine y is equal to, we can bring the multiplier up as a power, so really we have the power of a half on this 1 plus x squared, or the square root of 1 plus x squared, either is fine. Because this is a plus, the k acts as a multiplier there, so you've got ln of k times the square root of 1 plus x squared, or 1 plus x squared to the half. We can take exponentials of both sides, which are going to get rid of the natural logarithms. So sine y is equal to k times root 1 plus x squared. And finally, to make y the subject, you arc sine, or sine minus 1, the right hand side, so of k1 plus x squared. So either sine minus 1 or arc sine, either is fine. And that would be our solution for y in the form y equals f of x.